Hello everyone, today let's take a look at quantipus number 62, another question about Stirling numbers of the second kind. They're just asking us to prove a bunch of properties about Stirling numbers, so let's just get into it by looking at part A. So all it's asking us is how many ways can we separate m distinct objects into two non-empty unlabeled batches, so that's just going to be s of m comma 2. So we're splitting into two unlabeled sets. So first we're going to treat them as distinct, as if this were 1 and this were 2. Now we have m distinct elements to place into two distinct subsets. So there's going to be 2 to the m ways of doing that. But we know with Stirling numbers, we're concerned with non-empty and unlabeled batches. So we're just going to use inclusion exclusion, just like we've been doing this whole time. So I'm going to subtract off the cases where one set is empty. How many ways are there for me to do that? Well, there's 2 obviously because I have 2 different sets. So it's going to be -2. And then when I do that, I'm going to have m elements to place in one subset. And there's only one way to do that. So again, now that we know that the subsets are non-empty, we just divide by 2 factorial to remove the distinctness that we placed on them at the beginning. And that one was pretty simple. This is going to be our final answer, right? 2 to the m minus 2 on 2. We know that's just going to be equal to 2 to the power of m minus 1 minus 1, basically. And that's going to be our final answer for part A. Now let's look at part B, asking us to show that the Stirling number of m comma m minus 1 is equal to m choose 2. So what does this side of the equation mean? Well, it just means the number of ways to distribute m distinct items to m minus 1 non-empty and unlabeled subsets. So we have our m distinct items over here and our m minus 1 unlabeled subsets over here. These obviously all have to be non-empty because we're talking about Stirling numbers, so each one of our subsets is going to have to take one of these elements. So once I give 1 to each, right, I gave out m minus 1 of my elements, so I'm only going to have 1 remaining. So I can replace that remaining element in any one of my subsets, so one of them will have 2. My only partition is going to be 2, 1, 1, 1, 1, repeating, where there's going to be m minus 1 ones. Right, this right here is the only way to partition m objects into m minus 1 groups. Now, this is an integer partition. I still need to account for the distinctness of my objects. We've done this before. So how many times should I count this integer partition since it's the only one? Well, I have m objects and then I need to choose 2 to be in my group of 2 and everyone else will go in a group of 1. So it's just going to be m choose 2 and that gives us our final answer. Okay, now all that's left is the hardest one. That's going to be part C, which is showing the recurrence that s of n comma k is equal to k of the Stirling number of n minus 1 comma k plus the Stirling number of n minus 1 comma k minus 1. So to better understand this, let's just look at an example, the exact same thing that we were doing in quantipus number 94. If you remember, one of the things we had to do in that question was calculate s of 7 comma 4. So now imagine instead we wanted to calculate the number of ways to distribute 8 distinct items into 4 non-empty and identical subgroups, s of 8 comma 4. Well, how could we do this given this information over here? And as you can see here, I've drawn out all the partitions of 7 elements into 4 subgroups. Now we want to calculate the Stirling number of 8 comma 4, so that just means that we are basically adding one more unique element. So let's just say this is my 8th unique element. Let's call it x. So how can we add it onto one of these partitions? Because that's what we need to do to calculate s of 8 comma 4. So let's just go through every single partition and see how many ways we could add it. So for the partition 4, 1, 1, 1, I could add x to any of the 4 groups. So I have 4 different ways to add x to the partition 4, 1, 1, 1 because all of our subsets are non-empty. And I also have 4 ways to add it to this one for the exact same reasoning and 4 ways to add it to this one. So for every single partition where we have non-empty subsets, I can add it in 4 ways, right? So I'm going to take 350 times 4. Now what is 350? It was s of 7 comma 4. So if I add x to these partitions, right, then we get, what do we get? We get 4 times s of 7 comma 4. Now what happens if I instead chose to add my x to one of these partitions? Well, how many ways could I do it for each partition? Well, notice that there's one empty subset now, and since I'm trying to calculate the Stirling number of 8 comma 4, I need every subset to be non-empty. So I have to add x to the empty subset. So for each of these combinations, there's only one way for me to add x to it. So we calculated these numbers in quantipus number 94, but when you add them up, you get 301. So for each one of these partitions here, we have one way to add x, right? It has to go into the empty subset so that every subset is non-empty here. So we need to add on 301 to our total here to account for these cases. Now, what was 301? Well, we know from quantipose number 94 that it was s of 7, 3. Now, how many ways are there for me to add x to these subsets over here? Well, you can pretty clearly see that there's going to be 0 ways that keep every subset non-empty. So we're obviously going to count these 0 times here. So this right here is going to be our final answer. If we generalize it a little bit more, we get that s of 8, 4 is equal to 4 times s of 7, 4 plus s of 7, 3. And you can also pretty clearly see how this is going to generalize to this case where we're just working with a random n and k.